Quant Explained, breaking down quant finance concepts, quantum algorithms, and quantum computing. What is your name and what do you do?
My name is Rafał Pracht. I'm the CTO of finQbit. I'm the quantum researcher, and my work is to develop new quantum algorithms that can be used in the quantitative finance.
How does quantum computing potentially impact the field of cryptography?
Currently, the cryptography system uses two main classes of algorithms: symmetric key cryptography, where the same key is used for both encryption and decryption. These are powerful algorithms, but sharing the key between two parties without a security connection is problematic. The solution is asymmetric key cryptography, such as RSA, which uses a pair of keys. The public key is made available to anyone who wants to communicate secure with the key owner, while the private key is kept secret. The main idea behind asymmetric cryptography is that data encrypted with the public key can only be decrypted with the corresponding private key. To ensure that, we use a one-way function, the mathematical object that is easy to compute in the one direction, but computationally difficult to inverse, meaning it is very hard to reverse engineer the input from the output. For example, RSA is based on the mathematical difficulty of factoring the product of two larger prime numbers. This is where quantum computer come into the play. Peter Shor developed the quantum algorithm that shocked the classical cryptography's foundation in 1994. Shor's breakthrough demonstrated that a quantum computer could effectively factor large numbers previously believed to be an intractable task for classical computer. That means, on quantum computer, we can effectively reverse engineer the text encrypted by the RSA algorithm. The question is, should we be afraid now that somebody will overhear our encryption communication? Luckily, the Shor algorithm required much more powerful quantum hardware than exists today. So, maybe should we feel safe and ignore the existence of the Shor algorithm? Of course not. There is an attack called Harvest Now, Decrypt Later, in which an attacker intercepts encrypted data transmitted over a communication channel and stores it for further decryption. Later, the attacker gains access to a powerful quantum computer capable of running Shor algorithm and uses it to decrypt the data. Some data encrypted today could remain relevant and valuable for many years, even decades, into the future. So, we should now start our transition to post-quantum cryptography algorithms that are resilient to the quantum attack, especially because this process may take time and require a careful planning. But from my perspective, as a guy who design and create new quantum algorithms for finance, something else is much more important. First, the Shor algorithm has no business value. Of course, it destroys the current cryptography system, but doesn't create any new value or help us improve the world. Of course, except the quantum Fourier transform, which is a part of the algorithm. Second, Shor algorithms show us that on quantum computer we can do some tasks exponentially faster than on classical machine. To put it simple, there is a task that cannot be executed on a classical machine effectively, breaking the RSA, and we know how to do this effectively on the quantum computer. This is amazing. So, I believe there should be other tasks for which we can create quantum algorithms that are exponentially faster than the best classical algorithm. On the other hand, the Shor algorithm is the only one quantum algorithm with an exponential speedup. Considering that it was created 30 years ago, we can safely say that building a new quantum algorithm with an exponential speedup is not an easy task. Therefore, it's important to focus not only on the hardware development, but also on the creating new quantum algorithm that could positively impact the business and our life.
What is the quantum amplitude estimation algorithm, and how does it improve upon traditional Monte Carlo methods?
The quantum amplitude estimation algorithm is very important for applying quantum computing in finance. However, to understand why, we need to gain some understanding of quantum computing. First, the qubit, quantum bit, is the fundamental building block of quantum computation, analog to the classical bit in the classical computing. However, unlike the classical bit, which can be in one of two distinct states, 0 and 1, qubit can simultaneously exist in a superposition of both 0 and 1 state. But more important is what happens when we combine more than two qubits together. We have 4 possible states for the 2-qubit system, for 3-qubit system 8, and in general, for the n-qubit system, the vector state has 2 to the power of n elements. So, by adding a single qubit, our vector space is multiplied by factor 2. Now, quantum parallelism is coming into play. This is a fundamental concept in the quantum computing that refers to ability of quantum system to explore multiple computational paths simultaneously. So, using a single quantum operation, we can do it in all states at the same time. This is an amazing property, promising exponential speedup on quantum computer. However, there is a caveat. When measuring the superposition collapse, and we see only one state from the whole state vector. Here, the quantum amplitude estimation are going to come into the play. Suppose we can encode the solution to our problem in the probability of the additional ancillary qubit. In that case, we can use QA to extract the value from quantum computer with a square speedup compared to the standard measurement. For many algorithms, such encoding is simple. For example, QA is a building block of the quantum Monte Carlo algorithm and allow us to do operation on the quantum computer with quadratic speedup over the classical Monte Carlo. But how this works? Let's start with a Grover algorithm. There, we use an ORAC function to say which item we would like to find. The idea behind the Grover algorithm is to amplify the marked item while suppressing the unmarked item amplitude. The strength of the amplification depends on how many iterations we perform. This, combined with the quantum phase estimation algorithm, allow us to perform QAA. The idea is simple. In the QAA, we use a mark one state in our ancillary qubit, which is similar to the Grover. Next, we do a first iteration and encode the value in the phase, then 2 iterations, 4, 8, and so on. Ultimately, we use a quantum phase estimation to extract the value from a quantum computer with quadratic speedup.
For more on quant finance, join the CQF Institute now.